need to get or to create a transfer function. Differential equation. So yes.
Hola.
I guess wasn't obvious. So why were we studying transfer functions? Right? So if transfer functions are in modeling dynamic system, why are we studying them? Right? It's obvious. I believe. And what do I need to create a transfer function? Which is also obvious, right? So these two ideas are quite obvious. Okay? Now, the Laplace transform is doing what? How? Moves from the time domain to the complex domain. On how? Okay. That's what week of my life going nowhere.
Okay.
How are we changing from the time domain to the S domain? Codifying. A codification. Cool. What's a codification? So here I'm having behaviors of e to the s t. Okay? The solutions from the linear differential equations are just exponential. Okay? So in the complex domain, I only care about the s. Okay? Therefore, if s is complex, is e, well, it's imaginary, is e to the I something t, I omega t. Okay? So what is that coding for? If I have something like this, this is the coefficient, okay? Okay, of oscillation. Okay? So the idea here is if I have an imaginary part in this, on the complex domain, I will code it to the e to the I omega t, which will also be coded back as sine and cosine, right? Okay, if I have a negative real number, what am I coding back to? E to the something negative t. What is the shape of this function? The shape of this function is what? I need you to use control lingo. Lingo. Jargon. Language. A convergence. A convergence. Okay? It's convergent. Okay? If I have a positive value of the real part, what am I going back to? A divergence. Right? It's just the same idea of the exponential. So, do you understand exponential? If the answer is no, study up to exponentials, because the behavior of the exponential is coding, where I'm using the behavior of the exponential to code the information. So if this doesn't make sense to you, this won't make sense to you. Okay? If I have a complex number, and it is positive, it has a positive real part, what am I coding back to? don't care for the formula. I just want the shape of this. Divergent oscillations, right? Yeah. And if it was negative, divergent oscillations. Okay. These behaviors are for the zero input case, those or initial condition case. I'm not applying anything to my system. I'm just letting it be. Okay. Now, uh,
What would be the just the sigma plus I
which becomes e to the sigma t times e I omega.
what overlap?
Okay, this was covered in your differential equation class, and these ideas work only under certain restrictions. What are those restrictions? Laplace transform works in every single differential equation. No.
No, no linear.
In which differential equation can I use the Laplace transform?
Linear.
Okay, so this only works for what else? There are more restrictions.
Linear time invariant.
Yeah, we will be working with the LTIs. But this works with pretty much any linear system. Use the transfer function is not constant.
That time invariant means that the constants
The coefficients are constant.
were changing with the
Yeah, like the spring, coefficient of the band coefficient. Is the same. Okay. More restrictions.
From 0 to infinity instead of minus infinity to infinity positive.
What?
The
Say it in Spanish.
sí, de en la transformada de Fourier es de menos.
The integration limits?
¿Vale?
The integration limits?
Yeah.
Yeah, that's only the math formalities. I need scenarios in which I can use the Laplace transform for a given plant.
Una que no recuerdo, era eso de que tiene que tener un grado superior del. ¿Cómo se llama? Del numerador que
Yeah. But most importantly,
Las condiciones iniciales son 0.
yeah, that's the really important one. It only works if I consider initial conditions 0. Okay? What is it so?
Sí, sí, single input, single out.
The kind of systems are single input, single output. Okay? Cool? Whenever I can work with those things, I need another model.
Why do you need the initial condition?
Because when you're making the transform, the transformation of the derivative is what? For example, if I want this, this is equal to what?
Es
And you're missing something.
plus SF Riemann.
So we are not considering this in our transformation of our networks because we are assuming this value is zero. You say you cannot simulate your system in any initial condition. Okay? Okay. Now, out of the Laplace transform, I have where I get something like this. Okay, the transfer function, which is gain. Okay, right? That when expanding, I have something like this: a0 plus a1s plus a2s squared, blah 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 blah. An is n over b0 plus b1 s plus b2 s squared, blah blah blah. M is n, right? Okay, so after B.
And there the game is considered made, right?
Huh?
The game is considered already made.
The game is already there, and I can look at it as.
Okay.
There's another way we can write that stuff, and it has to do with the number of zeros I have here. So if B is 0 and B1 is 0, there's another way I can write it. That is S to the something, L times the polynomial. And this guy helps you to know what something values are going to be, because remember the integral part is important. It leads to state error of 0, and the more integrators you have in the system, you can achieve this error equal to 0 in more inputs than just the time. But that's so I just want to see, because as you are reading a lot, you are going to see sometimes like this is a type 0 system, or this is a type 1 system, or this is a type 2 system. The idea of that nomenclature is just the number of integrators. So a type 0 system has no integrators or no natural integrators. A type 1 system has one natural integrator. A type 2 system has two natural integrators. That's the idea. But this is more general.
And what's the difference between integrator and non-natural or
It just, yeah, mathematically it's the same. But the idea is they had it, but the system have it already.
okay.
And remember that one way to understand if a system has already integrators, if the system can hold its value or its position. So imagine you have a pendulum over a word, and then you apply 0 volts here. What's going to happen? If this is the word, and I apply 0 volts here, is it going to retain the position?
No.
Okay, so it has no natural derivatives. Okay. What about your AGP? It's here. You turn on the motors and then turn off the motors. Is it going to retain the position? Because it has a natural integrator. Physically, you are only controlling a speed. So to obtain position out of speed, you need to do what? So the physics, the physical laws are already integrating those into position, therefore the position retains the position. Because we are controlling the speed of this guy, and the natural physical world is integrating that speed into position. Whenever I stop the input, the position is retained. Well, no, that's it.
Yeah. Okay.
That's the idea. It has a natural integrator. Okay, so What is this called?
The characteristic polynomial.
Cool. And what are the properties of the characteristic polynomial?
It allows us to see how does the system compare.
Yeah. Okay, so well, I'm not going to say all, but a lot of the system's transient response okay. So if a lot of the system transient response is coded here, if I have a characteristic polynomial of the shape s squared plus 2s plus 1, who can tell me what's the behavior of this thing? Underdone.
It's convergence.
It's convergent. Yeah. So this is the convergent line, which I don't know what's the value, what is the convergent line. What are the poles of the polynomial?
-1.
Trust me, just by staring at the equations, you're not going to get out your calculators, open MATLAB, do something. I want answers.
The roots, -1.
The roots are -1. Okay, actually, this guy is typical high school exercise for algebra 1. This can be written as s plus 1 squared, right? So I have two roots at -1.
It's a critical.
Critically damped. Excellent. That's a critically damped system. Okay. I have repeated roots. What else? What's my settling time? 4 seconds. Between 4 and 5 seconds. Okay. So somewhere around here in 4 seconds. There's 2. 5 seconds. I have convergence of 2 and 1%. Okay? And from here on, I'm going to get basically my steady value. Okay? So I already know the steady state, when it's going to be achieved the steady state, and the transient state, what's the shape of the transient? The transient.
No state.
Is going to look something like this. And you do this. Okay? Good. So just by looking at this guy, I know what's going to happen. Okay? Now, what is going to happen with a system like this? What are the roots of that system?
It's also convergent.
So convergent,
The roots are -3 plus y. And -3 minus y.
okay? So what am I going to see? What kind of shape, what kind of system is this?
Overdone.
Over dam?
Underdone.
Sorry.
Remember damping means getting rid of the oscillation. So if there are still oscillations, I am under that. Okay? Settling time? What's the second time of that guy?
Is it over the wall?
Nope.
That's a forward three.
Okay. Okay, else. Who can also tell me?
Because they were part of the wall.
Yeah, and what else?
Tau equals 1.
Huh?
Tau equals 1.
Tau equals 1?
No. It is 1 over there.
Yeah.
1/3. Okay, so tau is 1/3, right? And I want a stabilization 4 times, between 4 and 5 times that guy. 4. Okay, so here, in 4/3 of a second, 5/3 of a second, I begin my steady state. And how much overshoot I'm going to be having? Once again, these kind of questions are not going to be answered just by staring at the whiteboard. What is the overshoot of that? What's the
El overshoot, ¿pero qué? ¿Pero qué pide?
Like you said it was underdone, right?
100?
How you put root in mathematics?
Whenever you have a question about a trade, just open the basic math assistant palette. Paletas, asistente de matemática básica. And you know, but you're going to be learning the shortcuts. The shortcut is control.
¿Contra what? ¿Qué es el antiinfector? Antiinfector aquí. Nada más me falta eso.
What do I need to do to get the overshoot? Huh? Just go back. I'm looking for the maximum overshoot. How do I calculate the maximum overshoot? Right? Okay. Good?
Underdamp.
Okay, so do I have the damping factor? Okay, How do I get the damping factor?
With the natural
Now
flow.
equals 4 over.
I'm going to say that 6 is equal to 2 times this guy. Okay,
And we know that the natural frequency is the square root of 25.
Ah,
so if you are, you have questions like, how am I going to, like, how am I supposed to know this? There is pretty simple, you know, this since I believe secondary school, you have 3 equations and 3 unknowns. You have a system of equations. What are my 3 unknowns? 1, 2, and 3. So I have 3 things I need to know, therefore I need 3 equations. That's right, as easy as it gets.
The object is 1.47.
This means natural frequency is going to be 5. Why am I not writing plus minus 5? Which would be correct.
le ponen número
Okay,
para
by
que siga
definition, the
siendo
natural frequency won't be negative. Therefore, from here,
Why is
there is going to be 3/5, right? What? What?
Why is not negative? Why is not the negative? Natural frequency.
Okay, oscillate at minus 1 hertz. Does that make sense?
No.
That's the reason. Okay, we need to be very logical. These are not stuff like, I need to memorize a lot of things. We don't. We just need to use logic. Does it make sense? Say I'm doing minus 5 cycles per second? No. We're counting on the real part, or the positive part of the real number. I have 1.5 cycles, that's okay. 3 complete cycles, that's okay. But having minus 3 cycles
ese
doesn't make
polinomio.
sense. Okay? Mathematically, it does make sense. Physically and conceptually, we cannot. Okay?
Es este.
I can do that method.
¿Este? Por eso. El 25. Ese es el que
Actually,
tiene.
from this guy is 0.09, what?
47.
470.
Ah,
Okay? So, this will imply 9.478%. Okay?
no se lo entendía yo.
So, if this is my convergence value, this is the 100%, right? And this is going to be 50, 25, about 12, so something like this. Okay? So, this is going to be hitting that value, maximum, right? Okay. And how many complete oscillations I'm going to be seeing in this space?
Es un formulazo. ¿Es el right? Y. No. It's 4 over. No. Is the settle time?
Huh?
The settle time?
No. How many complete oscillations I'm going to see in them? ¿Cuántas onditas voy a alcanzar a ver? Vamos a repasar, están viendo ecuaciones, escucho, es de beta, negro, ahí está. ¿Qué tiene que ver el número de oscilaciones con tiempo? Yo quiero una respuesta de 4 oscilaciones. ¿Por qué utilizaríamos una ecuación que da como resultados segundos? How can I use that?
1 over x.
Okay, so frequency is given in what unit?
Hertz.
No?
No.
Okay, so in 4 over 3 seconds, if I'm moving at a speed of 5 radians per second, how many radians would I be moving in that time interval?
20 over 3.
20 over 3, that's almost 7. 6.666. Okay? Right. 6.6 radians. How many complete oscillations are those? What's the value of a complete cycle of complete oscillation in radians? Okay, so 2 pi is equal to, well, it's around what value? 6 point? And I have 6.666, so I'm going to see a little bit more than a complete oscillation. Right? And if you can, like, notice what I just did, I didn't even use the calculator to tell you what's going on. Okay? You need to use your logic before you want to use your equations. Okay? So here I'm going to have almost one complete oscillation, a little bit more actually. Okay? And when is my peak time? This value is going to be situated where?
P over
Huh?
I was using the equation.
When is what the at what time I'm going to have that maximum?
P over the frequency of the damped. ¿Cómo se calcula la frecuencia del damping? ¿Cómo se calcula la frecuencia del damping?
0.78?
Yes.
What was the thing?
0.78.
5 volts.
¿Cómo se calcula la frecuencia del damping?
This is 1 second around here. Esto ya no me salió nada de escala. Okay, wait. Let me look like this. Okay? And this is at 0.78 seconds. Right? I decoded the time response out of these two values. Right? I decoded all of this information out of these two values, right? So we can see that the transfer from the characteristic polynomial is really important. If I understand, if I can control the characteristic polynomial, then I can say that I'm controlling the time response, right? Just look at the peak time formula. That's the idea of it. Okay, so those are the kinds of things that I'm going to be asking you. I don't even care if you know by heart the equations. But do you say, I'm being asked for the peak time. Therefore, I'm just going to look at my peak time formula. Okay? ¿Sí se lo punto de secretario? Okay. I just need confirmation from two guys that it's okay. One.
You control the time to go through the time or what you said before?
No, that what I want you to see is that we are decoding a lot of information out of just these two values. Okay, actually, these two values. With these two values, I got the shape of this thing. Okay, so if you can control the characteristic polynomial, it means you control the time response. So the idea is we are going to try to just control the characteristic polynomial instead of the differential equation system, because it's easier to control or to do math on the transfer function domain or the Laplace domain. Right? Okay. Ay,
Sí, ya quedó. Acá, ¿o no?
¿Alguien tiene una servilleta? No tanto sea.
Pues así, bueno.
Y de ahí,
Ese es el que se diferencia del toque, para que no se me acuerda. Y ya con eso la enfocas en impacto. El Big Time. Oiga, amigo, es tipo una fórmula. Pero no sabía dónde sacaba el WD.
por la raíz de. Sí, básicamente lo que hace es asume que eso va a oscilar, entonces implica que esa parte de la ecuación es negativa y factoriza el raíz de 1 y lo pone como I omega D. Okay, so then some guys studied, and this is also something you were supposed to see in your dynamic system class, is that I can have like really complex systems, but at the end of the day, I only want to understand them as a first order system or a second order system. Okay? So I only want to understand first order systems and second order systems. Okay? A third order system would be a first order system multiplying a second order system, and so on. A fourth order system can be four first orders or two second orders. And the idea is, out of these second orders, I'm particularly interested on studying whenever I have oscillations. Okay? Because if both of my roots are real, therefore I can understand them as first order systems. But if my second order system has imaginary numbers, then I want to study those imaginary numbers. Okay? Therefore, for this, I only care to study second order systems if they are underdamped. That's it. Okay? Overdamped systems, as you can see, they behave like first order systems. So the interesting part of second order systems are when they are overdamped. Okay? So the general equation of a first order system is what? What's the general transfer function of a first order system? Okay. What's the meaning of K? What's the meaning of tau? Okay. And there's another way to write this. That is K over tau is plus 1 over tau. Okay. What's the general shape of a second order system? Again, that's the square of the natural frequency.
S squared plus 2
Omega. I'm this close to ask the Greek alphabet. Okay. Right? Good?
Okay.
And also, these are all, and I'm going to emphasize this is important just if they oscillate. Okay? Therefore, if there's oscillation, I can use the functions I gave you. Only if this scenario is met, I can calculate for the delay time, the rise time, the overshoot. Okay? These values are only same time. I can calculate that even if it's a second order system with real parts. Okay, here I only have gain and ceiling time. I can calculate that. The gain, the ceiling time, and because I can calculate the ceiling time on a first order system, if this doesn't oscillate, I can still calculate the ceiling time. Okay, I can still calculate the gain of the system because those properties are shared with the first order system. Max me preguntó que por qué no puse el TSK. Pero el ser técnico lo puedo calcular aunque no oscile, porque es una propiedad que también tienen los de primer orden. La ganancia es algo que también puedo calcular aunque no oscile, porque es una propiedad que también tienen los de primer orden. Sobre impulsos, oscilaciones, eso no. ¿Ok? Good. Now, so the idea is I'm going to have systems of several orders, but at the end of the day, I just want to understand them as a first order system or a second order system. Additionally, my original systems or my case studies are systems with no zeros. Okay, because I can understand a zero as like a different input, right? A different input. Yeah, not necessarily. Okay, so what is the idea, or what is the first control idea to change the behavior of a system? If I already understand that the system is, or the transit behavior is determined by the transfer function, specifically by the characteristic polynomial, what can I do to change that characteristic polynomial into something else? What? Before? Eh? Change again. Okay, you are skipping something really important. Está dando por sentado algo muy fácil, muy importante. We need to close the loop. Okay, so that's okay. If by adding false and zero, or by changing the gain on the closed system, I can do that. Okay, but don't forget to close the loop. So the idea is I'm going to introduce something called the controller, okay, compensator, whatever, to modify the plant behavior. And the idea is, you could say that I want to modify the, and the idea is, if you add another zero or another pole, you will be changing the characteristic polynomial. If you add poles, you change the characteristic polynomial. But that doesn't guarantee that you are going to be getting the value you want. The only way you can check that you are getting the value you want is by making the comparison of the value you want from the set point, the reference value, what's another name? I think that those are more popular, and this. Okay. Now here I will have the dynamics of my sensor, right? But we are in a kind of a new scenario that this is complex enough to be adding anything but unit feedback. So if this value has the perfect signal, is the perfect sensor, the thing can, the value of my reading is going to be, well, the value of my reading is going to be the same as the actual value or the actual physical value. And this can be represented as what is the same, right? Multiplying by one is saying it's the same, and one thing, or what's another value for one, another name for one. This one is the unit. So this is a unit feedback control. Okay? I tell you because this couple of days I have been tutoring you. I see that you are not paying attention to these little things in the problems or in the problem statements. So this is a unit feedback. That is once again, it's obvious. It's really obvious.
I said that the root locus assumes that it is a unit feedback.
No. You can actually you can program a root locus to include the H of S.
Okay, but if you only input the system,
You put it, you see, if you input this, it's going to be it's going to assume that it's.
Okay.
So you can change that, but you need to like tell it to the.
That's,
Yeah, that's like it.
okay.
Okay? Because the idea is you're going to be using the closed loop system, right? Okay, so by definition or by some block algebra, what's the equivalent value of this thing?
Yes, over 1
This? Do you agree? It's wrong. Well,
Yes.
and if you want to have something else than a unit feedback control, then you can have H here. Okay? Only if H is explicitly something else than Y. Okay? Algebraically, it's all the same. Okay? It's just a little bit more complex algebra, but mathematically everything is the same, all the logic is the same, everything is the same. Okay? So as you can see, now the characteristic polynomial is going to be something else, right? Okay. How can I find where my poles are going to be? Okay. So as you can see, just by feedbacking and changing the location of my poles, but also the location of my poles is a function of whatever my compensator is, right? Okay, so what's the simplest control system I can use? Yeah, just use a gain. Okay? So in the simplest scenario in which I'm using a gain, this is going to look like K G of S, 1 K G of S. Right? So what's the tool that allows me to like see all the possible values of the location of the roots, locus, locations of roots? Literal, no me va a cansar nunca de decirles que esto es muy obvio. Okay? Everything is in the name, everything is in the properties. It's really simple. We just need to connect those ideas into one simple thing. Okay? So the root locus allows me.
The gain that MATLAB gives us from the root locus is the system gain.
No, it's the controller's gain. So what I'm doing here is I'm using a gain of the compensator, and this has the gain of the system. These are not the same.
So the gain of the root locus gives us
This. Okay, the plant is something that is static. It has its corresponding gain of something that I don't know, and what I'm moving is this value. Because the idea is, what can we change as control system designers? The controller or the plant? So what would be the value of analyzing how the system changes according to a variable that I cannot change? There's no value on that. And once again, simple logic allows me to go through that confusion. Because it's confusing. Everything is called gain here.
we are more than the other proportional part. Why does it still give us just one gain?
Because for example, for a PID, you have, well, for a PI, it's fast. For a PI, you have something proportional to the error and then proportional to the integral, which means you can write KP S plus KI over S, which means you can factor out something like KP. Actually, I think it's doesn't matter. You can factor out this, and then whenever you're doing your root locus, it depends on the location of this zero.
That it's given by AI.
Yeah. So.
Maybe it's like, let's say, constant for the.
And when you use control system designer, you add a zero, and you can move the location of that zero, that is moving this part, and then moving how far along the branches of the root locus you are going. So once again, you keep just moving along the branches using this guy, and these zeros and these poles are changing the shape of the branches of the root locus.
And we have a PhD also in something.
We have a second zero. Well, minus 0, 1, minus 0. This is a PID.
Okay, but even some just like modifying the zeros modifies the other two gates.
Yeah, but because the zero is the relationship of the gates.
Yeah.
When you are designing the root locus, you don't design KP and then you design the location of 0, 1, the location 0, 2, and the gate. And then you
change the.
and then back into KP, KI, Okay, good. So, what are some properties of the root locus? Okay, the root locus is going to have asymptotes. How many asymptotes do I have?
Where it depends on the zeros and the pole.
And what's that dependence relationship?
Sum of both amount of poles and zeros
The total number of poles?
minus number of zeros.
Zeros. Okay. Remember, zeros attract poles. Okay? Okay. In which directions are these asymptotes going to be moving?
2, 5,
It's really easy. If I have one asymptote, for one asymptote, what's the direction of that asymptote?
180 degrees.
190 degrees. Right? For two asymptotes,
90 and minus
90 minus 90. For three asymptotes,
60 minus 60.
180, 60, and 60. For four,
Like 145, 0. Oh, sí.
and there is an equation of that. Okay? Cool? Those little things are going to, we are not going to be calculating this stuff, but this is going to allow me to take to make some decisions according to what I'm asked for. So, if I have a system that is looking something like this or something like this, would imply that I can use an infinite k, or there's a value of k that is going to mess things up. In these systems, in 3 and 4, is there a value of k that is going to be messing up my system? Or not? No?
Yes, because the poles are going to go to the.
Yeah, that's what it is, because eventually these are asymptotes. They're going to the infinity. Eventually, no matter how to the left I am, eventually I'm going to be crossing to the right hand part of this.
We can determine that with Hurwitz.
And we can determine that with root Hurwitz. Okay?
And with the first one, second one.
Eh? Not necessarily. For example, it depends. If my system is going here from unstable to stable, yeah. But I can say it before it may happen or it may not happen. Once again here, if this is happening on the right side or left or on the left, there's no way I can do it. Yeah. It's mathematical law. Okay.
We have a job, but I don't know how to formulate it correctly, so I'm gonna try my best.
Okay.
We found out that the annual contribution of all the poles and zeros equals minus 180.
Yeah.
Why is that? I think it has to do with that, or I'm just.
From this part, the dynamic is found whenever my characteristic polynomial is equal to 0, right? Which means this guy is equal to minus 1, which means this is 1 that opens to 180 degrees. And because this guy is working like this and this is a constant, I can understand this complex number as the magnitude and the argument. They are the magnitude and the phase. Okay? So, because this guy is shaped in the form of a multiplication of k something s minus 0, 1, s minus 0, 2, etc., etc. And this guy is s minus 1, s minus 2, etc., etc., etc. This also means that I'm going to have k, a complex value that is a function of s that I'm going to be writing something like this. R1, well, R sigma 1 of s that opens at an angle that is also dependent on s. Right? Then the other one is going to be the same, and so on, so on. And this part on the denominator, I'm going to have the same thing, but for both.
Yeah.
And I'm going to change the name, the keep to make it a little more obvious. Okay? And because of the idea that I told you that multiplication is done faster when written in polar, this means that the value of this thing is going to be k times r1, r2, blah, 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 over rp1, rp2. This is going to be the magnitude. And the phase of k of s, which doesn't matter because k is constant, the same, is going to be the sum of all the values theta minus the sum of all the values theta.
And where does the minus relate?
Huh?
That has to be minus
My-
180.
Or 180. It's the same. It's the same angle. Yeah.
But, so you're making that the denominator equal.
The idea is the only possible values of s are those that fulfill those two requirements. This needs to be equal to 1, and this needs to be equal to plus minus 180 degrees. Because I want this. And to achieve this, the only way I can do it is if the gain of this guy, well, the magnitude of this guy is 1, and the argument is 180 degrees. So here's the tricky part, okay? I have told you many times that the ideas here are that the book was written, an older man in the book was written when we have like really low computational power. So instead of solving a really complex system of equations, we use the properties of the complex numbers in terms of magnitude and argument to simplify the calculations. Okay? But here the idea is simple calculations doesn't mean simple conceptualization. Okay? So what is easier to understand? Laplace, domain, or differential equations? Conceptually, what is easier?
¿Por what? Para él, ¿no?
What Laplace? That's not a conceptual understanding. Okay, so conceptually, what is easier to understand? What's going on the complex domain, or what is going on the time domain? What is easier to calculate? What is going on the time domain, or what is going on the complex domain? Okay, so simple calculation doesn't mean simple conceptualization. Okay, so because we wanted simple calculations, we needed to go to a little bit more complex conceptualization of just looking at the angles, looking at the magnitude. Now we have computational power. It's easier to just ask the computer in terms of my simple conceptualizations that I'm not going to be performing complex computations. At least me as a person, I'm not going to be doing that. Therefore, it's easier to understand everything in terms of the simple conceptualization and let the math be handled by. But that's
The reason why.
that's the reason why, and there are more properties. If you want the derivative of that thing, you will introduce another set of restrictions, and that's the whole idea. Or actually, studying these behaviors is the whole chapter about how to draw the root locus by hand. But we don't want to draw it by hand. It's really troublesome. I just are locus of the system, and I'm done. Okay? But this is not a it's not serendipity. Serendipity. Okay? Cool? Okay. So the idea, well, I'm going to give you this. Lisa's problems are really like really clear. The guy has troubles with grammar. Okay? So the idea here is just, or I want you to understand something. Writing clearly is really important because you now have suffered the consequences of someone not writing clearly, and it sucks. And the other is I need you to read more properly. Okay? Once I read the chapter, I understood what that guy was asking. Okay? So all that chapter, the idea of this is okay. You are a new engineer plant, and when you arrive to a system that is already controlled, but isn't performing ideas. And what they are asking of you is, please don't change a lot of the behavior of the system, but improve in some aspects. That's the whole idea of that. Okay, so there are also two ideas that I need you to really get. If you read the chapter, Lisa clearly explains that we have two kinds of systems, active systems and passive systems. What's the difference of active systems and passive systems?
Active systems. Bueno, ¿cómo? I don't know how to say it in English. Le da power.
Okay. Yeah, the idea is, what's the difference between an active filter and a passive filter? Yeah, so active filters have the capacity of inputting energy into the system. If you use a filter with a pants, the pants has its own power source, therefore it can inject energy to the system if needed. If needed. Okay? Passive systems cannot. Okay? They only store energy and release energy, but they cannot generate energy. Okay? And it says that if you want to use your compensator at two perfect perfect integrator or a too perfect derivator, you need to use active systems. If you don't, you need to like simulate or make a false integrator by adding a pole that is really close. And so to have a pole here perfectly sitting zero, I get active components. If I don't have active components or I cannot have active components, I'm going to use a zero a little bit, tiny bit on the left, and then it will act like an integrator. Okay, but this is really troublesome. Okay, and the idea is actually this is all engineering. Okay, because the only way I can guarantee a steady state error of zero is by adding an integrator, a two integrator. Okay, now think like 50 years ago, 60 years ago, think of the level of manufacture we have. Okay? And think about the level of manufacture we have right now. Have you ever seen those videos in YouTube where people have two pieces of metal and they put it together and it looks like one single piece of metal? You can even see the line. Okay, so think about the precision you need to manufacture that. Can you get that precision with something else that has steady state error of zero? Okay, so these ideas or of saying may sometimes need to use a lag compensator, which is the Mi Alegría PI, sorry. The lag compensator is the Mi Alegría PD, and the lead lag compensator is the Mi Alegría PID. We don't have those restrictions anymore. Okay, having active systems is really cheap. We have active systems in really small areas. So those controllers are really old. Okay? And sadly, you may encounter them in the Mexican industry, but it's not like really crucial to understand. The idea is the same. We can perform and do the analysis and see what's going on, but here I'm improving the steady state error, but I'm not guaranteeing the steady state error to be zero. That's the whole plan. Okay? Now, give me one of the problems you have. Because eventually you will saturate the system. So imagine you have line of 12 volts, okay, and you will have the integrator and an initial condition of voltage of zero. This guy is going to look something like this. As time goes on, if you cannot add energy to the system, how are you going to keep increasing in value? You need to add energy to the system to keep increasing in value. Okay? And actually, to have a true perfect derivative, you have an infinite amount of energy. Because eventually, for example, in a plant, once you hit minus 24 volts, then again. But the idea is, at least you perform
For that range, it is perfect.
and usually you design so you get out of that function. Don't go out.
¿Cómo se llama esa madre?
Bueno, ya llevamos 2 semanas en 1 hora.
Bien, qué padre. Qué padre. Sí, porque no. La clase pasada no sé porque nos iba a enseñar el.
La computadora.
No, el activo.
El lead,
No, él iba
ya,
a hacer el
que
activo y
hace
nosotros
es,
íbamos a hacer
si
el
aquí está el cero, pones hasta aquí.
Entonces él hizo el pasivo.
¿Eh?
Y nosotros hacemos el activo.
Ajá, o sea, si aquí está el cero, y el lead está acá, y el dash está acá.
De ayer para hoy me volvió una dieta.
Sí.
¿Quién se puso el Claro, que me encontré muchas veces.
No, Clase, pero no lo tengo Clase. Déjame entrar acá, hizo 10.
¿Por qué estamos descansando?
Ok, vamos a aprender a leer libros.
Pero, ¿lo vas a poner en Zoom? A ver.
Ahorita, ese libro de cuál es lo tiene usted también. Ahorita que me vaya.
Tal vez.
Viene, mi bien. Faltaste tú. Chanclas. ¿A quién falta ponerle 6
Es que depende de qué te vaya. Hay un libro que me gusta mucho que va a sentirse demasiado atrás, pero ayuda mucho a pensar en el pensamiento matemático, que es el Calculus de Spivak, Michael Spivak. Y en el primer capítulo les dice que es un número, pero de una manera que seguramente no lo han visto. Y técnicamente todo ese libro ya se lo saben, pero está escrito con las formalidades matemáticas que uno esperaría ya tener. Entonces, como ejercicio de mejora de pensamiento matemático y cálculo de Michael Spivak, S-P-I-V-A-K. Okay, so the idea here is really simple. Okay, this guy writes a little bit redundant. Okay, so here, designed via Rodolfo, he says we need to improve transit response. Improve transit response means I have an original transit response. Okay, so as we can see, it says the location of the post determine the behavior on the time domain. right? So poles at A and poles at B are what are described here. Does that make sense? For example, out of A and B, just by looking at this guy, you could tell me who is converting faster. Who is converting faster? The one that is on the left. So here, the convergence is happening faster, right? Okay, which is having more oscillations, A or B? So as you can see, a full cycle of A lasts this period. A full cycle of B lasts this, so which has a higher frequency. The one who completes this cycle faster, right? So the idea here is just what we already knew. The location of my poles determine the behavior on the time domain. Okay? And he says the error, once again, the ideas on actuality are we have no state error, okay? And we have two ways of compensating this guy. Okay? And here is the plan, or here is the idea that told you what was going on. Okay? Nice believed there was already an original controller on the plant, and we need to add this compensator so the original controller performs in a better way. Okay, and there are two types. That is in cascade. Cascade is the control work for each series. Okay, and the other is the compensation on the feedback. The idea is the same. Okay, the idea is I need to fool the original controller into believing that the error is something else, so I can perform better, right? And I have two ways of following that original controller that are, I need to take the error and use my compensator and change it. Or I change the feedback with the reference frame, and now this is a compensated error, right? In both ways, the only thing I need to do is feed a compensated error to the system. It's easier to analyze the system in cascade. Okay? And really read the chapters is quite clear, and make sure you are actually reading for understanding, like highlight ideas. If you don't understand something, like circle it out. They can note and ask you later. But what I don't like is our question like, how do I do it? I'm not a tutorial machine. Okay? I'm here to teach you how to think. So I will ask you for your ideas, and if you have zero ideas, then you have a really big problem. Okay? If you have ideas, then I can shape those ideas into the correct way of thinking. But if you come to me with straight zero ideas, there's nothing I can do. Okay? Because I can teach you how to do that specific problem, and then the next one you won't have any idea. Okay? So really focus on understanding. Okay? Now, here is saying what I told you. If I use ideal integral and using an EI, if I'm using not ideal integration, I'm using line compensation. But the ideas are quite easy. Okay? So here this explains a couple of okay, so the original system that we were working with was this one. Okay? Right? It's a third order system with our poles originally at these points, and I chose a case so that my system is performing like this. Right? But that have a steady state error that I wanted to improve. Therefore, I need an integral. And he says, okay, just have an integral. The integral part is what is going to be eliminating the steady state error. But that is adding another system, and the original behavior I had on the system is now unachievable, right? So that the way the system was performing just by adding the integral is now unachievable, which means I need to introduce this zero without, or at least in this kind of problems, without changing the original system, because that's the requisite. Okay, I'm not being asked for the best performance. I'm just being asked, don't mess with the performance in the system. Just change the state error, but don't mess with the dynamics of the system. That's the requirement. That's the design requirement. And as I told you, everything depends on the design requirement. Okay, the design requirements. Okay, if you are being asked to make it faster, then the set of requirements is different. If you want no oscillations, then the set of requirements is different. Now the requirement is don't mess with the original dynamics. Okay, so he says let's introduce a compensation. The compensator in the shape of k times a zero times an integral over an integral of 4, right? Which, as we saw, is the shape, the general shape of a pi controller. So he says, okay, look, I'm going to introduce the zero you wanted, and a zero really close to it, so when it gets attracted, then these guys behave kind of the same.
But they don't behave.
They don't behave the same, they cannot behave the same, but they are around the area. Okay? If you overlap the two root locus, you will see like this a little bit more open. Okay, if you overlap the two root locus.
Why whenever we integrate a compensator, for example, PD or PI, the gain reduces. For example, we have a gain of the natural system, then we integrate the PI or PD. In the case it was a PI, and we, for example, its gain was 150. Now it was 500, 550. So why does it reduce?
Mathematically, because this guy attracts zeros, and when you attract zeros, you need less smaller values of k to move along the line. The more concepts, a little bit for easier understanding, is you are now, what is easier for you to work alone or to work with a teammate? Okay, now the proportional has a teammate called ki. So a lot of the heavy work is done by ki and kb. The gain is you can leave off work, therefore it reduces its value. It's a nice way to understand it.
Less power, we can do the same work. Or better work.
Yeah, with less effort from you, the KP, you can achieve this kind of the same behavior. Okay? So that's the idea. That's very simple. Okay? Once again, if you read through the book, you will see that it's really easy. Okay? I wanted you to understand. I want to give you the tools so when you read the stuff, you understand. Okay? Now, as you can see, he uses faces or the angles, okay, to achieve this value. And this property it came from what I told you just now. Okay? The addition of the angles of the balls minus the angles of the zeros give me or should give me a multiple of 180. It actually is 180 minus 180, 360 plus 180, 720 plus 180. Okay, everything that ends up on the left side. Yeah, on the left side is But I told you these properties are for faster calculations. I actually do not need that right now. Okay? And that's the idea. For example, here it gives an example. Okay? So I have a plan with a game, and the thing is, think about it. The last engineer just got fired. No one knows what the K is. There's no way to find what that K is, but you know how the system performs. So how can I get what was that original K value? So that's the problem. Okay, well, the first part of the problem is I know this plant. The last engineer that worked here programmed a K, and nobody knows what that K is. But I know my system is performing in some kind of way. And the way that my system is performing is it has a damping ratio of 0.174. Okay? If I were to do the root locus on this guy, there are two ways I can understand what is going on. Okay? So, the first one is plotting the root locus. Okay? And then a little bit, a little piece of theory says that values that share the same damping factor are located along a straight line through zero. So everything in this line share the same damping factor. Everything in this line share the same damping factor. What's this angle so that the damping factor, the damping ratio is 1.174? Okay? I said
¿Pero qué pidió?
3. So what's that angle? 79?
Por eso que tiene que ver.
Point 97? Approximately
Pero es el ángulo.
80 degrees. Okay? With the current rules, I don't need to do the find the angle and okay, that's only trouble. Okay, you can plot this in the control system designer and find out. You can plot the R locus and the S grid, right? Okay, or what I want you to know is that this idea from the root locus, but we are not 100% certain on the actual value. We are limits, but by what we can see, or the resolution of the plot, or my pulse thinking. Okay, there's a way I can understand what is going on. No hay uno.
No, es arco coseno. A ver, otra vez. Va a ser igual.
Okay, so the open loop system es esto nada más, ¿no?
Pero este lo dio radiales.
¿Están de acuerdo que ese es mi sistema de lazo? ¿No? Ahorita ese sistema de lazo cerrado, lazo abierto, perdón, está multiplicado por una cara en la cual no tengo idea cuánto vale. Okay. ¿Cuánto es o cómo voy a calcular mi sistema de lazo cerrado? Que creo que un sistema.
Open loop system
Sobre menos A,
Esa fue muy buena. Ah, qué guapo. No me dejes.
Aquí nada más para fines prácticos, ¿no?
¿En serio? Mejor entro aquí a Zoom. Y le pongo que después si no, ahí no le sé yo.
¿Están de acuerdo? Ahora, mi polinomio característico depende de cuánto vale K. ¿Qué? Y eso se ve, y para sacarlo, a ver, mi polinomio característico es el denominador, y vamos a ponerle para que no se lo pongan es el denominador del closed loop system. Y quiero que eso me lo ponga un polinomio de ese. ¿Están de acuerdo?
No sabemos dónde está. ¿Por qué no estás?
Ah, espérame, es que estoy con otra cuenta. Déjame volver. Ahí está. Ok. Ajá. Ahora, ¿cómo se está comportando el sistema de manera real? ¿Cómo está comportando ahorita?
abierto.
Se sigue sin ver en el Zoom. Como chica.
No, esa es la mía. A ver, ya, así ya no me interesa. O sea, la pregunta no es, sepan usar el polinomio. Yo quiero que me dejen la lógica de lo que estoy haciendo. Este es mi polinomio característico. ¿Ok? ¿Cómo se está comportando realmente el sistema? El problema dice, ¿cómo se está comportando el sistema? ¿Ok?
con un damping ratio de 0.24.
Ok, eso significa que el damping ratio es una propiedad de qué tipo de sistema. ¿Cómo se ve un sistema de segundo orden en general?
Ese cuadrado más 2, un damping ratio, bueno, más W al cuadrado.
Ok, ¿de qué orden es mi polinomio característico?
Tercer orden.
Por lo tanto, yo les dije si es un tercer orden, ¿de qué está? ¿Cómo se conforma?
De otro polo.
Ya está el segundo orden, falta agregar el primer orden. Y aquí voy a poner como S menos el tercer polo de así, ya, lo que sea. Y esto es, digamos, el performance o el polinomio performance. Así se está comportando. O podemos decir que es el real característico polinomio, como quieran, da igual como bauticen esto. ¿Vale? Sí. Nada, para que se vea esto, el polinomio de ese. Si yo lo que estoy diciendo es que mi sistema se comporta como un polinomio real, ¿qué tendría que estar pasando? Si mi sistema se está comportando como el polinomio real, ¿qué debería estar pasando con esas dos ecuaciones? Pues yo las dos funciones las hago una ecuación. Es decir, el polinomio característico tiene que ser igual a esto. Y una manera rápida de hacerlo es, voy a hacer un set de ecuaciones donde el polinomio de s cuadrada, por ejemplo, igual a s cuadrada, el polinomio con s, y el que no tiene s es igual al que no tiene eso. Y una manera rápida de hacerlo, pues hacer un for loop muy rápido. Yo digo que el coeficiente del polinomio característico, que es un polinomio de s, el coeficiente de orden i, tiene que ser igual al real. ¿Y para qué órdenes quiero? Para i de 0 hasta todo cuadrado. Y esas son las tres ecuaciones que tengo que igualar, ¿no? Ahora, ¿tiene sentido cuántas ecuaciones tengo y cuántas incógnitas tengo?
Tres incógnitas, tres ecuaciones.
Incógnitas,
1, 2, 3, 4, 3. No, 3.
K, omega n.
No, pero ya el dumping ya lo tenemos.
Ajá. Te tengo que vaciar el pedazo de información que me dieron. Que este Z tiene que tener 0.0 Ahora sí, tiene sentido. El número de ecuaciones es igual al número de incógnitas. ¿Desde cuándo se sabe en esa regla? Primaria. ¿Cada cuándo revisan que cumplen esa regla? ¿Cada cuándo revisan si están cumpliendo esa regla? Ok, primer error, ¿no? Porque si tienen información que va desde la primaria a secundaria, que se utiliza para validar. De verdad no tengo idea de esto, se cuenta cuántas veces las he corregido, simplemente que no concuerda eso. Y nadie se toma la molestia de checarlo. Es una regla básica, es lo que les digo, estas matemáticas básicas, solo apliquen las matemáticas básicas. ¿Ok? Entonces, este es un sistema de ecuaciones que fácilmente lo puede resolver la computadora, yo no. Esas son las tres cosas que tengo que checar. Esas son mis tres incógnitas. Pues lo que le estoy diciendo ahí es resuelve el sistema de ecuaciones hechas por las ecuaciones que ya definí y dime cuánto vale omega n y cuánto vale el tercer polo. Ahí está. De estas dos soluciones, ¿cuál es la correcta?
¿Cuál es el tercer polo?
La de abajo.
¿Cuál es el tercer polo? Pues no sé, es lo que estoy calculando.
Ahí va a ser la segunda.
La pregunta es, ¿por qué hay un tercer polo? Porque si mi polinomio característico es de 3 y mi criterio de diseño es lo que lo dieron por un segundo orden, yo no puedo hacer la comparativa.
¿Le añades un polo?
Pues sí, porque
Para
si
que sea el mismo.
es lo que digo, un sistema de tercer orden está dado por uno de primero y uno de segundo. Entonces ese de segundo, bueno, puede ser 3 primeros, pero ese de segundo orden, pues no lo puedo comparar con un tercero, ¿no? Por ejemplo, si les digo, los dedos de sus manos, ¿cuál equivale, o cuál es el equivalente de los dedos de sus manos a los dedos de los pies? El pulgar parece el dedo gordo, ¿no? Porque hay una relación 1 a 1. ¿Cuál es el equivalente de sus dedos para su pierna? ¿Su pulgar es su muslo? Para empezar, es el mismo número de elementos, ¿no? O sea, tengo que comparar 5 cosas con 3. No se puede. ¿Ok? Y ya, la ganancia, ¿cuál de estas dos posibles soluciones es la correcta? Vamos a buscar salón porque es una correcta. Pero váyanme diciendo.
La de abajo.
La
¿Por qué?
segunda,
Porque no tiene una frecuencia natural negativa.
Porque otra vez no tiene sentido decir que hay una frecuencia negativa. Sí. No, lo sustituí, pero lo recalculé las dos para que con una característica voy a hacer a esta y la ecuación será. ¿Dónde creo que iba a jugar? ¿Se debe? En alguno de los
sácala, güey.
¿Acá la estaba vacía?
Al chile no sé. Pero sácala. Verga, ayer intentaba eliminar. ¿Sabes que no puedo tener una granizota? ¿La vas a finalizar o...? No es fácil luego adelantarle y... Ah, no, puede hacer lo que quiera. Un saludo. Tiene 14. Va a decir que opinión. Dice que preguntan por el penal.
No, la vamos a buscar otro, porque la plataforma que soy tenía para revisar salones, descubrí que esa plataforma era exclusiva de los servidores del CEN. Y hay una directiva de Monterrey a pagar los servidores del CEN. No, ya sé. Yo sí, ya sé. O sea, dijiste que yo estaba en como chingan. Yo sí caché.
Hola amigos, estamos aquí en un día más de Control con Mike. Acompáñenos al siguiente salón.
Está en vivo. Hazle así y lo tapo.
Sí. Nos vemos en el siguiente salón. Ahí está.
Gio, ¿por qué dicen que eres el malilla, güey?
No puedo pausar.
La tabla del mal.
¿Qué le caso ahí?
Mi papá.
¿Cómo se pausa esto?
No lo pauses si quieres.
Oye,
Solamente pon la descripción. A partir de cierto minuto hubo cambio de salón hasta tanto y ya.
está saliendo, ¿eh?
No me dejes, Oscar, por favor. ¿A cuál se van a ir?
No sé.
Quería traer hoy solo una mochila, pero los apenas trajeron las cosas. Wow, qué cambio, ¿no? Sergio,
Ok, ¿cuánto vale A? Para que estas dos cosas sean iguales, ¿cuánto tiene que valer A? ¿Cuánto tiene que valer B? ¿Cuánto tiene que valer C? Facilísimo. Una bien.
una bien.
Así es el examen, profe.
Para que estas cosas sean iguales, ¿cuánto tiene que valer A?